Let's discuss question number 48, 49, which is fetched a common data question. Okay, so a Bell-Coleman refrigeration cycle is used to produce 10 tons of refrigeration. So refrigeration. So this is from test 7 from refrigeration, so thermodynamics. So refrigeration capacity is 10 tons, and we know that each ton is 3.5 kilowatt. Is what is 1 ton. So this is 35 kilowatt. Okay, the cooler and the refrigerator pressures are 4.2 and 1.4 bars. Okay, so how do you draw in a TH diagram? In a TH diagram, if you look at it, it's basically a Bell-Coleman cycle is nothing but air refrigeration cycle, and it works on the reversed Brayton cycle. So it is something like this. You have these two. So it's something like this. You're doing the work here, and this is takes these are constant pressure lines. So it takes 1 to 2. Let's start from here. 1 to 2, you're compressing the refrigerant. 2 to 3, you're ejecting the heat. 3 to 4 is again just expansion valve. With that, it will be a small compressor here, small pump, small turbine actually, because it's a reversed. And 4 to 1 is basically heat absorption, or heat actually taking heat from the surroundings. That is nothing but from your refrigeration cabin. So 4 to 1 is evaporator. So this is your evaporator, and this is your condenser. Okay, so these are the things. So now this pressure is given as 1.4 bar, and this is given as 4.2 bar. Okay, and that's the thing. So now, as it works on a reverse Brayton cycle, so each of the process if you just apply, and so you can derive an equation for COP. Now COP is nothing but the heat, the desired effect by net work input. Okay, now desired effect is nothing but your 4 to 1, how much heat it has taken. Let's say this is Q1, so this Q1 by work input. Now this if you derive, actually, and I mean you can actually come back with the Brayton cycle also. In a Brayton cycle we were interested in the heat addition, so by work input. So in that case it is Q addition, W by Q addition is the efficiency, which we know the efficiency formula. So efficiency we know the formula in terms of RP. So 1 minus 1 by RP, gamma minus 1 by gamma is what is the efficiency of reverse of the Brayton cycle. But now what we are interested in COP. Now COP is Q1 by network input. Now Q, so but here in terms of Q addition, which is, so this efficiency can be written as, so W plus Q addition can be, this is Q addition, just only the signs of the heat transfer have changed. So this Q addition is nothing but Q1 plus W. Okay, so these are the, so basically what I'm saying is this, I am driving the COP formula in expression of COP expression because I know that it's a reverse Brayton cycle. So I'm just using the fact that in a Brayton cycle this is the case. So from this I need to find Q1 by W, and this if you try to find Q1 by W, just reciprocate and find out, you will get a value called 1 by RP gamma minus 1 by gamma minus 1. So this is what I'll get the COP. So this value I have to, so it's only the pressure ratio which I am interested. So RP gamma minus 1 by gamma minus 1. So how much is the RP? Now RP is 4.2 by 1.4 into 0.4 by 1.4 minus 1. So this value comes out to be 2.7. So the answer for 48th bit is B for the 48th bit, and as it is a common data question, let's continue 49. Now what is asked is the mass flow rate. So okay, so let's look at the temperatures what are given. Now T1, temperature at the inlet is T1, which is given as minus 20, so minus 20 plus 273, that is 253 Kelvin. Then air is cooled in the cooler, so condenser is what he is calling as a cooler. So at the end of the thing it is T3, which is given as 45, so that is 273, which is nothing but 318 Kelvin. Okay, so I know T1, I know T3. Okay, now I need to find T2. So this 1 and 2 is isentropic process in an ideal sense. So T2 by T1, obviously you have all those PV cube is C and TV cube minus 1 is C, and from these two, because it's air only, ideal gas, so I can relate between T and P, and this is what I get. T2 by T1 is P2 by P1 whole power gamma minus 1 by gamma. So I know P2 by P1 it's 3. It's basically P2 by P1, I know the pressure, and I know the, so P2 by P1 is 3, 4.2 by, and this is whole power 0.4 by 1.4. So this value, basically I know T1, so from this I can get T2, which comes out to be 346.4 Kelvin. So once I know T2, okay, now the idea is to get T4, because I know the refrigeration capacity, so I know how much heat it takes in 4 to 1. So I need to find T4. Now how do I find T4? Let's apply 3 to 4 is also an isentropic, so let's apply T3 by T4 is P3. In fact, I need not find T2. T2 is of no use. So straight away let's go to T3 by T4 is P3 by P4 gamma minus 1 by gamma. P3 by P4 is 3.4 by 1.4. I know T3, so from this I can get T4, and the T4 value comes out to be 232.3 Kelvin. So I know T4, I know T1, and the enthalpies per unit mass. What is the enthalpy increase? H1 minus H4, because it's air I can use Cp T1 minus T4, and mass into mass flow rate into H1 minus H4 is what is the heat that is taken from the refrigeration space per second, and that is nothing but your refrigeration capacity, which is 35 kilowatts. So mass flow rate 35 kilowatts, so I'm just writing 35 into 10 power 3. H1 minus H2 specific heat is 1.005 into 10 power 3 kilojoules, and T1 minus T1 is 253. So let me write here, Cp is 1.005 into 10 power 3, and T1 minus T1 is 253, T4 is 232.3, is 35 into 10 power 3. So this comes out to be 1.684, and I need to just multiply with 60 to get in kg per minute, because what is 1.684 is kg per second. So this comes out to be 101.606 kg per minute, and so roughly it is 101 kg per minute. So the answer for this is A. So this is a straightforward problem. Only thing is, first the COP calculation, which is nothing but a reverse Brayton cycle. So a direct formula you can just derive from the normal Brayton cycle efficiency, and 48 is just getting T4, because we know how much heat is absorbed there. So answer is A for 49. Thank you.